Hi everyone and welcome back to Physics 2B. Today we're going to be covering electromagnetic waves or E&M waves. So let's get started with what are these waves. This is a radiation that's in the form of waves of electric and magnetic energy. And we have felt this or seen this in our day-to-day lives, including the warmth from the sun, x-rays that we need to use in the doctor's office, microwaving foods, and even the colors that we can see with our eyes. So these are all different forms of electromagnetic waves, and we'll look at those further in detail down the line here. So let's start with the ideas of Maxwell's equations. Now, I don't have the actual equations listed here because they are um, a little too mathematically advanced for what we're interested in. And so these are statements for what they are, okay? And Maxwell, he got all of these, he kind of rounded up all of these equations that other scientists have done, other physicists, and gathered them and applied them to electro electromagnetic waves. Okay, so the first one he has is going to be related to Coulomb's law and therefore Gauss's law for electricity. And it's a couple of different ideas here that electric field lines start on positive charges and end on negative charges. Also that an electric field is defined as the force per unit charge on a test charge, and the strength of the force is related to the electric constant, epsilon naught. The second one here is Gauss's law for magnetism, or that magnetic field lines are continuous, have no start and end, or end. No magnetic monopoles are known to exist, and that the strength of magnetic field is related to the magnetic constant mu naught. Okay. The third here involves Faraday's law of induction and also Lenz's law, that a changing magnetic field induces an electromotive force, or an EMF, and an electric field. Also that the direction of the EMF opposes the change in the magnetic field. Okay. The fourth and final one here is Ampere's law, that magnetic fields are generated by moving charges or changing electric fields. So again, these were all already defined, but Maxwell gathered them all, and put them to use towards electromagnetic waves. So this is his theory, but let's first talk about this production of an electric field due to an alternating current. So this here is AC, or alternating current. This is a wire, like an antenna, and I probably spelled that wrong, antenna. And at time t equals to 0, we have some electric field, but as time goes on, that alternating current will cause the electric field to change. Okay, so at 1/4 of some time t, we see a quarter of what's happening. So from here to there, we see that the electric field has decreased. Okay, let me try to draw this. And then to a spot where it looks like it's 0, right? Or it might be 0. Then as time goes on even more, it has completely switched directions. So now it is going the opposite direction, again, due to this being alternating current. And we continue all the way through one whole time period, t, and we see that it ends up back at the same original amplitude, okay? So here and here are the same amplitude, okay? So due to this alternating current, we can look at our electric field and see how it changes. And I think it'll be on the next slide, but this is what we call a sinusoidal wave, okay? So this shows that we have some sort of wave-like motion, okay? So his Maxwell's theory states that electric and magnetic forces are not separate, but different manifestations of the same thing, an electromagnetic force. Now, these E&M waves, they're oscillating electric and magnetic fields, like we just saw with the electric field. They're capable of exerting forces on charges great distances from sources, and so they might be detectable from some distance, right? So maybe if there's something going on in another part in the universe, we might be able to detect it, okay? So that's the whole idea here. They also propagate or move at some speed, okay? And that speed we define as c, or the speed of light, and that value is equal to 1 over square root of mu naught times epsilon naught, which is 3 times 10 to the 8th meters per second, okay? So this propagation is the fact that this wave is moving away from our source at some velocity, and that velocity is equal to c, or the speed of light, okay? All right, so what does that have to do with magnetism? Well, we know that electricity and magnetism are very tightly bound, and when we have an electricity, or some sort of electric current, we will have a magnetic field. So up here at the top, we see that we have the same antenna, okay, and an alternating current, and we have our E field, and therefore have some sort of magnetic field B, okay. And what we notice is that the B and the E field are perpendicular to each other, okay. So again, following Ampere's law, the alternating current in the antenna produces a magnetic field, like we have seen in the past chapter. As that current varies, the magnetic field varies, just like we were looking at the electric field varying in the previous slide. And so now we get this alternating B field here. Okay, notice that similarity. So another thing that is noticed is that the E field and the B field are exactly in phase and perpendicular to one another, and to the direction of propagation, meaning we are moving along this axis here. Say that's the x-axis. Our B and E field are both perpendicular to that axis, okay? So let's see. I know I skipped a thing here. Oh, they're in phase. So when waves are in phase, they will be increasing and maybe decreasing at the same spot. So we have that increase up to some peak, and then decreasing, or maybe the peak is more over here. There we go. And then decreasing back, going into the negative, and so forth. So they're exactly in phase with each other, okay? Again, moving with some velocity c, which is the speed of light. Because it is propagating in the direction that is perpendicular to both E and B, we say that it is a transverse wave. Okay, so it's a transverse wave because E and B fields are perpendicular to, I'm going to say, the velocity or propagation. Direction of. Okay. Okay. So this ratio of the E field and the B field strengths in any electromagnetic wave is equal to c, or our speed of light, velocity. Okay. All right. So, given that information, let's start with an example. What is the maximum strength of the B field in an electromagnetic wave that has a maximum E field strength of 1000 volts per meter? So we just said E over B is equal to C. Agreed? Yes, that's what we just said. So we can rewrite this as B is equal to E divided by C. Not too bad. So we'll have our E field strength. So come on. Oops. There we go. 1000 volts per meter divided by C, which was 3.0 times 10 to the 8th meters per second. So we can put that into our calculator and we get a value of 3.3 times 10 to the negative 6th, and this is in Teslas. It's a little bit sloppy. Let me fix that. Okay. So, this would be what? Mu Teslas? Whoops, sorry. Mu Teslas, maybe? Okay, so this is a very small B field for that maximum E field strength. Okay. All right. So let me go ahead and pause here and then we'll continue talking about the electromagnetic spectrum.